Welcome to Lecture 46. This is not a lecture in which I'm going to introduce all kinds of complicated physics or do all kinds of complicated calculations, although we will do a calculation or two. It's a lecture in which I'm going to introduce just one idea, and it's going to be a very simple idea, disarmingly simple, so simple that I'll be able to state it in just a single English language statement, no equations, no mathematics, just a simple statement. And yet it's a statement that's going to turn our ideas of space and time on their heads. And it's the statement that's going to resolve the ether quandaries that we've been looking at in the last couple of lectures. Let me remind you where we stood at the end, basically, of the 19th century. We've got physicists scratching their heads because their attempts to apply a mechanical view of the universe to electromagnetism, in particular to the propagation of electromagnetic waves, light, failed. It failed because all attempts to detect Earth's motion through this ether, this mysterious problematic substance that pervaded the whole universe, failed. It left us with the question with respect to what does light move at speed c. We can no longer answer the ether. We know from binary star observations we can't answer the source. So what is the answer to that seemingly simple question? Whole centuries, millennia of common sense ideas about space and time actually hinge on that answer. That problem was resolved by a single individual who was probably the most brilliant physicist of all time, perhaps second after Newton, and that, of course, was Albert Einstein. Now, before I talk about Albert Einstein, let me just point out that he didn't develop his ideas in a complete vacuum. There were others who came close, in particular Lorentz, whom I mentioned in the last lectures, having come up with that contraction hypothesis. The French physicist and mathematician Poincaré is another example of someone who came close to relativity, but neither of them really got there. Neither of them really cut through to the simplicity that is the idea of Einstein's theory of special relativity. That's what I'm going to deal with in this lecture. Let's begin by taking a look at Einstein himself and what some of his other achievements were, and then we'll move in and focus on relativity itself. Albert Einstein was born in 1879 in Ulm, Germany. He had an interesting childhood, going back and forth a bit between Germany and Switzerland. He gave up his German citizenship. He was unhappy with some of the attitudes in Germany. In 1900, he received his so-called teaching diploma from the Zurich Polytechnic Institute. He was not a great student, but he was not a terrible student either. He could not get an academic job following his graduation from the Polytechnic, as could most of his classmates, and the reason Einstein couldn't had to do with a certain attitude he had that didn't allow any of his professors really to recommend him highly for a teaching position. He became instead a patent examiner with the Swiss Patent Office, which was actually a very good job for him because it allowed him to think in his spare time about physics. It allowed him to deal with real physical objects, physical things people had invented, and he was extremely productive during this period. He also became a young father at about this time. He actually had been a father somewhat earlier, but this was the first child born into his marriage to Mileva Marek, who was a fellow student of his, a fellow physics student, one of the few women studying physics at that time. And here is Einstein with Hans Albert. This is actually a rather rare picture, but there he is with his young son, Hans Albert, in about the year 1905, which was when he was 26 years old, and that was Einstein's miracle year. During that miracle year, he published seminal papers in 3 very distinct areas of physics, any one of which could have won him the Nobel Prize. So 1905, Einstein's miracle year. What went on in that year? On April 30th, he published his doctoral dissertation. His doctoral dissertation was entitled A New Determination of Molecular Dimensions. That doesn't sound very exciting, but this is around the year 1900, and the reality of atoms and molecules was not yet firmly established. On June 9th, he published a paper which is the predominant one that won him the Nobel Prize, although others figured in it also. And this was on the quantum nature of light, something we'll deal with after we get done with relativity. And the paper was entitled On a Heuristic Point of View Concerning the Production and Transformation of Light. Again, doesn't sound very exciting, but it introduced one of the key concepts in quantum physics. On July 18th, he published convincing proof that atoms exist. On the movement of small particles suspended in stationary liquids. Doesn't sound very exciting again. But the July 18th paper, along with his doctoral dissertation, were in sort of the same area. They dealt with the random motion of small particles, and they gave a proof that small motions of tiny little particles, but not atomic-sized particles that you might see under a microscope, were caused by the particles being hit by random fluctuations in the smaller molecules and atoms that you couldn't see. And that was the convincing proof that atoms exist. On September 26th, he published the paper that describes to the world for the first time the special theory of relativity. It's not called the special theory of relativity. It's not called my new theory of space and time. It's called On the Electrodynamics of Moving Bodies. And that title tells you how intimately connected relativity is with electromagnetism. And in this course, I've tried to stress electromagnetism. I've talked a lot about electromagnetic waves, light as an electromagnetic waves, the ether as the medium in which electric and magnetic fields were supposed to be stresses and strains. There is an intimate connection between all those ideas and the special theory of relativity. And finally, on November 21st, he publishes what's basically a footnote to special relativity. It's the paper in which the idea E equals mc squared, probably the most famous equation in the world, was first introduced. And we'll see later on, as we're studying relativity in the next few lectures, that E equals mc squared isn't really the most general form of the equation, and this is an equation that is much misinterpreted. But it's nevertheless an important idea, and it was given in a paper whose title is a little more transparent than some of these others. Does the inertia of a body depend on its energy content? So that's Einstein's miracle year. The important paper to us here is the September 26th paper, The Special Theory of Relativity on the Electrodynamics of Moving Bodies, and I want to spend the rest of this lecture on the ideas that are in that paper, or rather the one simple idea at the heart of that paper. And I'm going to show it big and bold because it's such a simple and such an important idea. It's called the principle of relativity. It's not an idea that's new to Einstein. Galileo and Newton knew of a principle of relativity, but Einstein generalized that principle and basically made it his own, and it becomes the heart of what's called the theory of special relativity, and I'll be distinguishing the special and general theories as we go along. And here's what it says. The laws of physics are the same for all observers in uniform motion. Period. That's it. Contained in that single English language statement is everything you can say about the special theory of relativity. Take off the in uniform motion, and you've got basically the general theory of relativity, but that gets a little more complicated, and we'll get to that. But this idea is really, really utterly simple, and that's all it says. What does this mean? It means no matter who you are, no matter where you are in the universe, no matter how you're moving, as long as your motion is uniform and unaccelerated, not changing in speed or direction, then you do physics experiments and you will determine exactly the same laws of physics I do. Now you might say, wait a minute, can't do physics on Earth because it's in circular motion, and I can't do it in an airplane. Where can I do it? Well, that gets a little bit involved, and in fact, it gets so involved that some of that is what leads Einstein to general relativity, some of those questions. But let me just say, the Earth's accelerated motion, such as it is, and some of it doesn't really count and some of it does, we'll see why shortly, the Earth is close enough to in uniform motion that we can talk about the Earth as if it's a reference frame in uniform motion, a so-called inertial reference frame. So we're going to beg for now the question of how we know for sure we've got a reference frame in uniform motion, and that question is going to come back to haunt us. But let's assume that we do. And then if I'm in uniform motion and you move relative to me uniformly, so you are not accelerating relative to me, but you're moving relative to me, then the laws of physics that you determine by experiments will be exactly the same as the ones I do. Another way to put this is, if we each do the same experiment, we'll each get exactly the same result. All the laws of physics. Here's how Einstein put it himself in his paper on the electrodynamics of moving bodies, published in 1905, the paper that brought the world special relativity. Here is the beginning paragraph of that paper. It is known that Maxwell's electrodynamics, when applied to moving bodies, leads to asymmetries which do not appear to be inherent in the phenomena. Take, for example, the reciprocal action of a magnet and a conductor. The observable phenomenon here depends only on the relative motion of the conductor and the magnet. Now let me pause there and talk to you about exactly what Einstein is describing here. He's describing an experiment I did back in lecture 36, and we got a little clip of it here playing. It's the experiment where I thrust a magnet at a coil of wire, and I found that there was an induced current that flowed in that coil of wire, and I measured that with a meter and so on. Then I did the same thing by holding the magnet stationary and moving the coil of wire near the magnet. And the same thing happened. And you might say that's obvious. But it isn't nearly so obvious, because in one case we describe that by saying there is a changing magnetic field associated with the moving magnet, and changing magnetic fields make electrical effects. In the other, where we're removing the conductor, we've got free charges in the conductor, the charges are moving in a magnetic field, they experience a magnetic force, and that's what gets the current going. The observable phenomenon here depends only on the relative motion of the conductor and the magnet. The asymmetries, that is, the different descriptions, one involving the magnetic force on moving charges, the other involving the electric field ultimately generated by a changing magnetic field, those are the asymmetries. They don't seem inherent in the phenomenon, namely the generation of an induced current from the relative motion of the conductor and the magnet. So all that matters is the relative motion, and he's referring explicitly to that description of induction when we move a magnet near an electrical conductor. Then Einstein goes on. Examples of this sort, together with unsuccessful attempts to discover any motion of the Earth relative to the, quote, light medium, for which you can read ether, suggest that the phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. So what's he talking about here? He's talking about the failure to detect Earth's motion through the ether. Now, there's an interesting history of science issue here. It is not 100% clear that Einstein knew of the Michelson-Morley result. Historians of science still debate that. If he didn't, all the more power to his genius for coming up with this idea without that seminal experiment. I mean, there were plenty of other pieces of evidence that pointed to problems with the ether. But that clinching experiment that measured so sensitively the fact that Earth didn't move relative to the ether, Einstein may or may not have known about that. The phenomenon of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. What is he saying there? He's telling us for the first time that, hey, it's not just Newtonian mechanics that doesn't depend on your reference frame. It's also electromagnetism. And it's the implications for electromagnetism that are going to lead us deeply into what relativity really tells us about the world. The phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. Now, what does this mean, and what are some alternative ways of saying this principle of relativity? Well, I've just said it. The laws of physics are the same for all observers in uniform motion. But there are plenty of other ways to talk about it. There's no preferred frame of reference. There's no one state of motion in which you must do physics if you want to get it right. There's no preferred reference frame. The ether doesn't exist, is part of the implications of relativity. Concepts of absolute rest and absolute motion are meaningless. It is meaningless for me to say, I am moving and you're not, or I am at rest and you're moving. Those are meaningless statements. Anytime you catch yourself trying to say something like that, you're not speaking in relativistically correct terms, as it were. Concepts of absolute rest and absolute motion are meaningless. I am moving is a meaningless statement. I am at rest is also a meaningless statement. Only relative motion matters. That's the only thing we can talk about. We can say, you're moving relative to me, I'm moving relative to you, but we can't say I'm at rest and you're moving, or vice versa. And to give an example I talked about in the last lecture, I said you could play tennis on a cruise ship, or for that matter on a spaceship, even if it's moving at 99% of the speed of light relative to Earth. And I better add that thing, relative to Earth, because if I just said moving at 99% of the speed of light, that's a meaningless statement. I can only talk about relative motion. And you can play tennis and the laws of physics work the same in either of those cases. We talked about that last time because we knew that Newtonian physics obeyed a relativity principle, that Newtonian physics didn't care what reference frame you were in as long as you were moving uniformly. Now we add something. You could also put some tea in a microwave oven and heat it up on that cruise ship or on a spaceship, and that's a statement that the laws of electromagnetism, Einstein said, electrodynamics, as well as mechanics, have no concept of absolute rest, have no preferred frame of reference. Alternate wordings of the principle of relativity. What are some implications of this principle? The laws of physics are the same for all observers in uniform motion. It applies to all of physics now. That's why I said all of physics, not just mechanics, not just electromagnetism. All of physics come under the umbrella of special relativity. Mechanics, that's no surprise. We already knew that you could eat those peanuts on an airplane and you didn't worry about the fact that it was whizzing along at 600 miles an hour. it becomes a surprise for electromagnetism because everybody thought before there was only one frame of reference, the ether frame, where electromagnetism was valid, where Maxwell's equations would give you the correct results, where you would measure c for the speed of light. Remember, in lecture 40, we got into the mathematics a little bit and we determined that there were electromagnetic waves. The wave speed was determined by that cross-fertilization, if you will, of changing magnetism making electricity and changing electricity making magnetism. And we expressed that in Faraday's and Ampere's laws, which I've written here in a kind of calculus form. But the point is, this quantity I've circled, the magnetic constant over 4 pi times the electric constant, that turned out to be the square of the speed of those waves, and that speed was predicted by Maxwell's equations and by the numbers in there to be the speed of light, c. So the principle of relativity is telling us that Maxwell's equations are valid in any frame of reference, and that means that the speed of light is the same for all observers in uniform motion, even if they're moving relative to each other. The speed of light has to be the same for all uniformly moving observers, even though they're moving relative to each other. And I'd like to describe for you an experiment that brings that point home. Before I do that, let me make one sort of philosophical historical point. Einstein, in his paper, actually presented two principles. He called them postulates. One was the principle of relativity, as I've described it here, that the laws of physics are the same for all observers in uniform motion. The other was, what he said was a seemingly contradictory statement, that the speed of light was independent of its source. Philosophically, though, you do not need both of those. The principle of relativity is enough to cover it all, and here's why. Because the principle of relativity says Maxwell's equations have no preferred frame. They're equally valid in any uniformly moving reference frame. And therefore, the statement that the speed of light in vacuum is c, 3 times 10 to the 8 meters per second, the square root of mu naught over 4 pi k, that statement has to be valid in all uniformly moving frames of reference. Let's take a look at what that might mean. So let's think how we might measure the speed of light. So here you are standing on a roadside and there's a traffic light, and the traffic light is going to go on and it's going to send out a flash of light, which I've represented here by some wave crests. And I'm going to give you a really nice clock and a really nice meter stick, perfectly made, very accurate, and I'm going to ask you to time with your clock how long it takes the light to go exactly 1 meter with your meter stick, and I'm going to ask you to calculate on that basis what the speed of light is. So here comes the light by you, and you calculate the speed of light, and you get for the speed of light exactly 299,792,458 meters per second, which is the exact speed of light. Now, a friend goes by in her sports car, and she's going at 70 miles an hour toward that traffic signal. What does she do? We hand her a measuring stick, a perfect meter stick, and a clock, and we ask her to do exactly the same experiment, timing how long it takes light to cross her meter stick and calculate a speed, and she gets 299,792,458 meters per second also, even though she's moving relative to you. And you might say, well, her velocity is really small, so maybe that's just an error. So you got another friend who's a pilot, and he's going by in a big airplane, 600 miles an hour, gets the same speed of light with the same good clock and meter stick. And finally, you got another friend who's an astronaut, and she's going by at half the speed of light. And you ask her to do the same measurements, and she does, and she gets 299,792,458 meters per second. We all get the same value for the speed of light, even though we're moving relative to each other. How can that be? Well, maybe I'm special. Maybe I'm the only one, or you're the only one. You're standing by the road. You should get the right speed because you're standing on the road where the traffic light is. The traffic light and the road are irrelevant. The speed of light does not depend on its source. In fact, from your point of view, you're standing still and the spaceship is going by you, but the spaceship can equally well say it's standing still and you're going by the other way at half the speed of light, and yet it understands, if it understands relativity, that you're going to get the same value for the speed of light. How can that be? How can it be that we get the same values for the speed of light, which we have measured with our clock and our meter stick? And these are perfectly good clocks. We bought the best we could get. They're guaranteed to be accurate. How can it be that we got the same value for the speed of light? It can only be if somehow my meter stick and your meter stick and the astronaut's meter stick are not measuring quite the same thing. They're all measuring accurately, and the clocks are not quite measuring the same thing, and the clocks and the meter sticks are different in such a way that they all get the speed of light. You may say, oh, the spaceship's clocks in meter 6 are screwed up because it's moving so fast. But you can't say that. That's relativistically incorrect. The spaceship has an equal claim on being able to do physics as you do. Nobody is right. Nobody's got the right frame of reference. And yet they all measure the speed of light as the same value. And the only way that can happen is if their measures of space and time are different. Space and time cannot be absolutes. Space and time simply are not what we thought they were with our common sense. There is no immutable time flowing unaffected by anything throughout the whole universe. Newton actually made a statement to the effect that there was. He was wrong. Measures of time and space are simply not absolutes. They cannot be. That cannot be consistent with the simple statement that the laws of physics must be the same for all observers in uniform motion. Let me give you one example where simple Newtonian ideas go awry because of this fact that measures of time and space are not absolute. And we'll look at more of these examples in coming lectures. So let me give you a very simple example. How do you add velocities of things? So here I've got a spaceship and it's going past the Earth at 80% of the speed of light, 0.8 c. And inside it is a little spaceship, and the little spaceship is going past the big spaceship or through the big spaceship at 60% of the speed of light. And I'm going to ask the very simple question, how fast is the little spaceship moving relative to Earth? And the answer is absolutely obvious. It's 1.4 c. How did you do that? Well, let's get a little bit abstract about that. It's called, in fact, Galilean velocity addition. You didn't know the word for it. You just knew it made obvious common sense. I'm going to add 0.6 and 0.8, get 1.4. Let's call u an object's velocity relative to some reference frame, which I'll call s. And in this case, I'll make s the reference frame of the Earth. So u is an object's velocity relative to Earth. Let's call u prime an object's velocity relative to some other reference frame. In this case, the big spaceship, and I'll call that frame s prime. So u prime is 0.6 c, and v then is the velocity of s relative to s prime, or s prime relative to s, it doesn't matter, and that's the 0.8 c that the spaceship is moving relative to Earth. There's v, and you said, well, it's clear, u is u prime plus v. 0.6 plus 0.8, 1.4. Not right. It would be right if measures of time and space were the same in all these reference frames, on the Earth, in the big spaceship, in the little spaceship. But they aren't. We've just seen that they can't be. Measures of time and space must be different in ways that we'll come to understand in coming lectures, but they must be different in order that all these observers measure the same value for the speed of light. What actually happens in this case? Well, I'm not going to go through the whole derivation of this math at this point, although we could do that. What happens is this. There is a relativistic velocity addition law, and it takes into account this variation in measures of time and space in different frames of reference. So again, I'm going to use the same terminology. U is going to be the object's velocity relative to some reference frame S. U prime is going to be the object's velocity relative to some reference frame S prime. And again, the object in question here is the little spaceship. The reference frame S is the reference frame of Earth. The reference frame S prime is the reference frame of the big spaceship. And v is the velocity, the relative velocity between those two reference frames, which is the 0.8 c. And here's what the formula looks like, again, with no real justification or derivation. But what it's got in its numerator is that simple Galilean velocity addition that you would have expected by common sense held. You simply add the two velocities. But then it's divided by this factor in the denominator, which is 1. And if it were just 1, we'd get the Galilean answer back again. But it's 1 plus something. It's 1 plus the product of these two velocities, u prime and v, one of them being 0.6 c, one of them being 0.8 c, divided by c squared. So if those quantities are small compared to the speed of light, if either of those velocities is small, that little correction term in the denominator is going to be small. And we're not going to see a result that's much different from the Galilean velocity addition. But when those speeds get up near the speed of light, the relative speeds I'm talking about get up near the speed of light, then that correction becomes significant. It makes the denominator bigger than 1, and it reduces the added velocity from what you would expect it was from simple Galilean Newtonian considerations. Let's actually do a calculation like that here on our big monitor. Okay, so here we are. We're going to figure out how we add the velocities of these objects in that example I just gave. So here's frame S, the Earth. Here's our big spaceship, frame S prime. The relative velocity between them is 0.8 c, 80% of the speed of light. And we want to know what the speed of that small spaceship inside the big one is relative to Earth, applying this new relativistic velocity addition formula. So let's work it out. It's the Galilean result, 1.4, 0.6 plus 0.8, divided by this correction term again. Well, that's 0.6 plus 0.8 divided by 1 plus 0.6c times 0.8c over c squared. 6 times 8 is 48. So that's 1.4c, what we would have got in the Galilean mode of thinking, divided by 1.48. You can see that 1.48 is bigger than 1.4, so the answer comes out less than c. In fact, it comes out in this particular case 0.95c. By the way, that's our first hint at something that's really important in relativity, and that is that no material object can go relative to any inertial frame at a speed greater than c. And this is not a proof, but this is a statement that, in fact, that is true in this particular case. You might think, well, I know how to get to going faster than c. I can kind of leapfrog by going, tenth of c relative to something, a tenth of c relative to something else, tenth of c. Keep adding that up. Can't do it. Relativistic velocity addition puts an end to that. Won't let that happen. So relativistic velocity addition is going to preclude our going faster than c. Well, let's wrap this up, and then I'm going to give you a challenge. We've really seen one big idea. We've seen the idea that was one of the ideas Einstein posed in his miracle year, and that's the principle of relativity. The laws of physics are the same for all observers in uniform motion, and if you remember nothing else about relativity from this course, that's all you need to know. All the rest follows. It applies to both mechanics and electromagnetism. It requires that all uniformly moving observers measure the same value c for the speed of light, and that's impossible unless space and time are not absolutes. The big takeaway message here. Maxwell's electromagnetism, it turns out, is relativistically correct. We don't need to make any changes in electromagnetism, surprisingly. Relativistically perfect. No corrections. We do need to make corrections for Newtonian mechanics, it turns out. Although relativity already worked in mechanics, it wasn't Einstein's special relativity, and the Galilean velocity addition being incorrect is the first hint that we need to make some fairly subtle but significant changes in Newtonian mechanics. And there's the Galilean velocity addition being replaced with the relativistic velocity addition that includes this correction term. Okay, before you go, if you're so inclined mathematically, let me pose you a dual challenge here. The challenge is, first of all, I'm going to consider a situation now in which I have two spacecraft approaching Earth at 0.75 c each. And I want to know, if you're sitting in spaceship A on the left, what's the speed of spaceship B relative to you? You would think naively 1.5 c, but no. In B, I want you to do the adding velocities example again, but now replace the small spaceship with a laser beam, and of course a laser beam, being light, goes at speed c, and I would like you to show that as long as the large spaceship's speed is less than c, the laser beam speed relative to Earth is also c, and that will confirm that the speed of light, according to relativity, has to be the same for all observers in uniform motion. Okay, work on your challenge. I'll come back with the solution. Okay, here's the solution. Let's let A, spaceship A on the left, be frame S. Let's let Earth be frame S prime, and we want to know the speed of the right-hand spaceship B relative to frame S. Then V and U are the same. They're both 0.75 c. We apply that relativistic velocity addition formula. Up in the numerator is the 1.5 c we would have expected, but downstairs is a correction. 1 plus 7.75 squared. By the way, all the c's canceled because I expressed this as fractions of c, and the answer comes out 0.96 c. So you didn't get 1.5 c by having them head at each other like that. Let's do the same thing here. This will do the math symbolically. Here u prime is c, so wherever I see a u prime, I put in a c. I get c plus v over 1 plus cv over c squared. Let's work that out. Put it over a common denominator. I got c plus v over c. Let's flip that the way we do fractions over fractions. We got c plus v times c over c plus v. The c plus v cancels, and the speed of light is the same for observers in both those uniformly moving reference frames, even though they're in motion relative to each other.